start the session. Today we're going to deal with radiation physics, how an X-ray machine is constructed, what are the parts that has been used, and what are the properties of X-rays that we can use to record images, or you can say radiographic images. We have two types of recording medium that you are going to learn in the next session after talking about radiation biology. Okay, so radiation physics, a part of which we have discussed in the lab, so that you'll be able to understand the today's sessions much better. Okay, so atom, as we all know, it's the smallest unit of the matter. It has a positively charged nucleus and negatively charged electrons surrounding the nucleus in fixed energy levels, which is called as orbits. Okay, so the nucleus, it has protons, which is positively charged, and neutrons, which is neutral, that means no charge. So the net charge of nucleus becomes positive, whereas the electrons are negatively charged and they spin around the nucleus, and it is kept close towards the nucleus with the help of a force, and this force is called as electrostatic force of attraction. Okay, so what do you mean by this electrostatic force of attraction? So electrostatic force of attraction means it is the force that holds a positively charged particle, that is the nucleus here, and the negatively charged particles, that means the electrons here, together. Okay, so they are held together with a force of attraction. Okay, so this force of attraction is called as electrostatic force of attraction. Okay, now whenever there is a force between two objects, there will definitely be an energy created which binds these positive and negative charges together, so that energy which binds them together, it's called as the binding energy. So why do we want to know about the binding energy? So if you want to remove one electron from this atom, okay, you have to give an energy more than the binding energy of this electron to the nucleus. So for example, as you can see some numbers here for the K shell, L shell and M shell. So K shell, that is the closest shell to the nucleus, has vacancy or space, you can say, for 2 electrons. It will not hold more than 2. Whereas the L shell has vacancy for 4 electrons. It will not hold more than 4. Whereas M shell, it has vacancy for 8 electrons and it will not hold more than 8. So these energy levels are called as shells or orbits. They also have a specified number to amount the binding energy. So binding energy, as I said before, it is the energy which is required to remove one electron from its orbit. Okay, so this binding energy is the energy that is binding this electron towards the nucleus. So if you supply a binding energy more than this, you can remove this electron from the K shell. So here is the numbers: 70 kilo electron volt. Okay, so that is called as the binding energy of K shell. So if I want to remove an electron from the K shell, I have to give 70 or more than 70. Then only this electron will come out. If I want to remove an electron from the L shell, I have to remove an or give an energy of more than 12,000 or equal to 12,000 to remove an electron from the L shell. Likewise, I have to give 3,000 to remove an electron from the M shell. Okay, so if at all one electron moves out of any shell, for example, let's say that the electron from the K shell was moved out by supplying a binding energy of 70,000 electron volt. So, in such a case, if this electron is going to go out, okay, if this electron is going to go out of the atom, it will create a space, an empty space. So, what happens? This higher energy or higher orbit electron, to be precise, it is going to come down to this empty space. So when it comes down to the empty space, as you know, that there is some energy difference between the orbits. So this electron will lose some energy and it will come down to this orbit. So that is important for the production of X-rays. Okay, so to concise it or to make it short or summarize, we have an atom which has a positively charged nucleus and a negatively charged electron, which is held together by a force of attraction called as electrostatic force. This force creates an energy between them, which we call as binding energy. So, binding energy means the amount of energy that we have to give to remove an electron from the orbit. Okay. Now, if you want to remove an electron from its orbit, okay, you end up making it an ion. That means for some radiation, they are called as ionizing radiation. Okay. So an atom is usually neutral. That means it doesn't have any charge. Okay. Neutral atom means the number of protons, the number of electrons will be the same. So as you can see here, both of them are 14 and 14 in number. Okay. So if any external radiation, for example X-rays, it comes inside the atom and removes one electron from the atom, then here it becomes 13 negative charges, and for the plus charge it is still 14. So what happens? The plus charge is more, that means the proton is more, so the atom becomes positively charged ion. And the electron which goes out, it becomes the negative ion. Okay? So if an atom is neutral, there will be equal number of electrons and equal number of protons. If one electron is removed, the electron which goes out, it becomes the negative ion, and the atom in which there is more number of positive charge becomes a positive ion. And this process is called as ionization. Okay, the process by which radiation can result in the formation of a negatively charged ion and a positively charged ion. It's called as ionization. And both the negative ion and the positive ion together, they are called an ion pair. So, your question now for the session that will start: what is an ion pair? Okay, so you have options: negative charge, A is negative charge, B is positive charge, and C is both negative and positive charged ion. So, what is your answer? You can type in A, B, or C. So, what you can speak up?
Negative.
Okay. Yes, Alia? C. Okay. What about Dalal? Dalal and Lulu? Okay. Dalal? Dalal is not here? So we'll move on to the next session, that is the types of ionizing radiation. Okay, so we have a particulate radiation and an electromagnetic radiation. So particulate radiation means the radiation travels in the form of particles. It is usually emitted by radioactive elements. Okay, whereas in the case of electromagnetic radiation, it means that there is movement of energy through space as a combination of and electric and magnetic fields. Okay, so that is why the name electromagnetic radiation, because it has both electric and magnetic fields. Okay, so an electromagnetic radiation usually travels together, both in combination. So when this wave travels together, the energy travels or is propagated. Propagated means moves in the form of photons. Okay, so electromagnetic radiation has both waves and it also has packets of energy called as photons. Okay, so photons are nothing, just packets of energy. It does not have any charge, it does not have any mass, you cannot see them, and it travels in the speed of light. Okay, so it travels faster. Now, electromagnetic spectrum. So, electromagnetic spectrum, it shows the relationship between photon wavelength and energy. Okay, so it's like the visible light spectrum. You know that there are seven colors in the rainbow, and these colors are arranged according to their wavelength. Okay, so when we start with violet, indigo, blue, green, yellow, orange, and end with red, it starts with a shorter wavelength. Okay, shorter wavelength means the waves are like this, and it ends in a longer wavelength. Okay, like this, big waves. Okay, so when the radiation is arranged in the form of wavelength or frequency, you can call it as a spectrum. So now if you see this image, you can see there is radio waves, microwaves, infrared waves, visible light, UV rays, X-rays, gamma rays. Okay, and you can see that there is some numbers written which represents the wavelength, and also it represents the photon energy. So always remember, the energy is high when the wavelength is small. So, meaning to say that when you see the X-rays, these X-rays fall into the criteria of shorter wavelength, high energy radiation. Okay, so X-rays falls under this criteria. Whereas the others, if you move towards the left side of the spectrum, you can see the visible color ends in red, then infrared starts, microwave starts, and radio waves also start. Okay, so this is longer wavelength. So longer wavelength has low energy, and higher a shorter wavelength has higher energy. So X-rays belong to shorter wavelength and high energy radiation in the spectrum of electromagnetic radiation. Okay, so you can see here the medical science imaging, radiotherapy is here, dental radiography is here, x-rays and gamma rays is here. You can also see the term soft x-rays, and you can also find hard x-rays. Okay, so soft x-rays, again the wavelength is going to decrease, and hard it's going to increase again. So properties of x-rays: it travels in straight line, it cannot be focused to a point, it is a great disadvantage. So in the x-ray machine we make it a point to address this issue. Differentially absorbed, the solid, liquid, and gases, they are going to absorb it differently. Solid will absorb the maximum, then the liquids, and the last is the gas. Causes fluorescence. Now this is another important property which we are going to utilize in extraoral imaging. Okay, the fluorescence properties we are going to utilize in the extraoral imaging. Okay, so in the extraoral imaging, what we have to remember is that some materials like phosphorus, okay, can take up the X-rays and start emitting visible light like green light or blue light. Okay, so this property of X-rays is called as fluorescence. It can take up X-rays which is invisible and it will give out visible light. Okay, it is harmful for the living tissues. So when we make the X-ray machine, we have to take this point into consideration. High energy waves, it is good because we can take the diagnostic X-rays that we want and we can see what is the problem inside that area of the body. Then high energy waves, no mass, no charge, travel at the speed of light but invisible. Okay, so which is the property of X-rays which we can use in extraoral imaging? Okay, which is the property of X-rays which we can use in extraoral imaging? Okay, so what is it? Is it A? Is it radiation? Or is it B? Fluorescence. So, what is the property of X ray which you can use? Yes, Suvad?
Type 1.
Hmm? Is it A, radiation, or B, fluorescence?
Fluorescence B.
Okay, so B, it's fluorescence. Okay, so again, Dalal, you have missed the second question. So this means that you are not present here for the session and you'll not get your attendance until you are here or you have a valid reason of missing the session. Okay, so now you are missing two questions. Great. So, parts of the intellectual machine. So, you have seen the lab and you have seen the parts very clearly. We have a control panel, which is the heart of the X-ray machine. We have support arms, like the limbs in the body. We have legs and we have the hands. Then we have X-ray tube head, which is like the head of the body. And then we have a dental X-ray tube inside the X-ray tube head. It's like the brain. So both the brain and the heart is required to produce a diagnostically uh, acceptable X-rays. Okay, so X-rays, the dental X-ray tube, it forms the brain, which is supported with the help of X-ray tube head, and then support arms are there. Control panel forms the heart, which regulates all the current through the second. Okay, so on the tube head you have a cylinder shaped device. It's called as the cone or the PID or BID. Now this parts we have labeled it during the lab time, but I will just go through it once again. We have the dental X-ray tube that we are going to discuss first. So in dental X-ray tube, you can see there is a gray shaped area that has been marked here. That is the leaded glass tube. Okay, so it's the leaded glass tube. Now, the leaded glass tube is open at one area, which means that it doesn't have a lead lining. So, this is called as the unleaded glass window of the X ray tube. Okay, the whole tube is made of glass except one small window which is unleaded. The whole area is made of leaded glass. Okay, so unleaded glass plus the leaded glass gives you the dental X-ray tube. Inside that there is vacuum space, that means there is no gas molecules inside, which can collide with the electrons and result in discharge of energy. Then we have the cathode, which is negatively charged. It has two parts, a cup-shaped structure called as focusing cup. It's made of molybdenum metal. And we have a filament, which is made of tungsten. Now we use filament at two areas, one on the cathode and the other on the anode. The filament is made of tungsten because it has a low vapor pressure, it has a high melting point, and it has a high atomic number, and at the same time it is going to be drawn into thin wires, and if you do like that it is not going to break. Okay, so because of that we can use tungsten at the filament. Now the other area where tungsten is the target. Okay, so we want the x-rays, or the electrons, to move from the filament area, that is the point A, to anode area, that is in the region of the target, that is point B. That means the aim of the electron is towards the B, so B is the target of the electrons. Okay, so targeting means to aim. So electrons go and hit on the tungsten target once it is produced. So its name is tungsten target. Okay. Now the negatively charged cathode with the filament and the cup. What happens here? The normal line voltage is 110 or 220. It is supplied into the filament. Now there is a problem, as we discussed in the lab, that we do not want this much voltage. We want only 3 to 5 volt or a maximum of 10 volts. So we use the step down transformer to lower the voltage, and we supply to the filament. So filament gets heated up and it starts emitting ions. This process is called as thermionic emission. That means with the help of thermal or heat energy, ions are produced. So once ions are produced, all these electrons are going to club around in front of the cathode with the help of the focusing cup, which help to focus the electrons. If focusing cup is not there, all the electrons are going to hit on the target at random speed. That means we will not get a diagnostically quality radiograph. Okay, so the electron cloud is formed in front of the cathode, which is going to be pulled towards the anode and hit on the tungsten target in an area called as focal spot. So focal spot is the area where the electron from the cathode is going to hit on the tungsten target and X-ray is produced. Now this focal spot, if it is large, the sharpness is less. So before the anode used to be straight, but now it is at an angle, so that the focal spot size decreases. If there is a decrease in the focal spot size, then there is an increase in the sharpness. So once the X-rays are produced, only 1% produced as X-ray, and the rest 99% is produced as heat energy. So we are going to use a stem made of copper, which is the good conductor of electricity and good conductor of heat. So here we use a copper stem, which is the gray colored area. So this is used to help remove the heat from within the dental X-ray tube to outside the tube. If the heat is within the dental X-ray tube, it can result in melting of the tube. So now the heat energy moves outside, and then there is this insulating oil which continuously circulates around the dental X-ray tube. Okay, so by doing this circulation, it is going to remove the heat energy to outside the tube. Of course, it is going to be supplied with the coolant as well at the end. Now, the oil, as you know, it has to be contained. So we are going to use the container metal housing of X-ray tube head. So this metal housing is made of lead again, which will help to prevent any radiation from going outside. So the lead metal housing of X-ray tube is given or made to contain the insulating oil. Now, we want the X-rays to be focused whenever it gets out of the X-ray machine. So we focus the X-ray machine at one point, that is the unleaded glass window. By giving just a window and leading up all the glass tube, we made sure that the X-rays that is produced comes out only through this point. Now, when the X-ray comes out to this point, it is going to come out from here. So if you had made a blockage over here, that means the metal housing is completely closed. So the radiation will not come out. So we have to open it. When we open it, the oil is going to come out. So in order to seal it, we are going to put a tube head seal, which is not made of the lead material. If you use lead for the tube head seal, then no radiation is going to come out. Okay, so tube head seal is placed now. Now when the x-rays comes out, it meets at two regions. One is the unleaded glass window and the other is where the surface of oil and the metal barrier of the tube head seal. So some amount of filtration takes place which filters the long wavelength low energy x-rays because it gets absorbed, and it allows the high energy x-rays to pass through it. Okay, so two points inside the x-ray machine which act as filters: unleaded glass window and oil and metal barrier. After that we have to put an added barrier. Okay, so added barrier is used to give filtration that is not attained by the filtration given by the X-ray tube head from those two regions. Okay, so we provide the added filtration. If a machine works at 70 kilovolt, then the added filtration is 1.5 millimeter thickness of aluminum. Okay, likewise, if a machine operates more than 70, we give 2.5 millimeter thickness of aluminum. Now, lastly, we have two parts. One is the lead collimator, which looks like a CD. It's made of lead. It has a central hole, which can be circular or it can be rectangle. Based on the shape of this collimator, you have to also select the shape of the PID, or you can say cone or position indicating device. It's also made of, or you can say lined with lead, and then it's used there. So what happens once the X-rays comes after filtration? It is going to travel through this PID or cone and come to the other end. Okay, so collimator basically reduces the dose of X-rays. The position indicating device helps to aim the X-ray beam towards the patient. Okay, so what we just discussed, we have it everything in the slide so that you can have a look at them. Okay, what is the collimator? What is the function of collimator? What is the shape difference? Okay, so this is how a collimator is going to reduce the amount of exposure reaching the patient. So you can have a circular collimator which looks like a CD, a rectangular collimator, and also a triangular collimator as well. Always remember, circular collimators have more exposure than the triangular ones. So the difference is around 55%. So rectangular collimator gives you only 55% of the total radiation that is given by the circular one. Filtration, as we discussed, it removes the low energy, longer wavelength X-rays. Then, okay, just one second. Yeah, the next one is the PID or the cone, which helps to aim the X-ray beam towards the patient. Okay, it is used to aim the X-ray beam. Now, control panel timer. So, timer, it is built in circuit to regulate the volume, of current passing through the circuit per minute. Okay, so this timer, when you press the switch on, there is a current passing through the circuit towards the cathode, and then voltage will pass towards the anode. Okay, so basically, the radiation which comes out from the X ray machine is called as primary radiation. The radiation which interacts with X rays is called as the radiation which interacts with the matter is called as secondary radiation. And any type of secondary radiation which hits the matter and which moves in a different path, which we call it as scattering, it is called as a scattered radiation. Okay, so primary, which comes out of the X-ray machine; secondary, which hits the matter; scattered, which hits the matter and it gets diverted. So interaction of the X-rays with the matter, it can be basically of three types. Okay, that means it can get absorbed, it can get scattered, or it can get both scattered and resorbed. Now there are some factors which controls the X-ray beam: exposure time, tube current, voltage, filtration, collimation, target to patient distance, etc. So what you have to know from this slide is that the quantity of X-rays produced can be changed by altering or changing the exposure time, tube time, that is the tube current, and the voltage, because all of them represents quantity. Only the kilovoltage potential, that is the tube voltage, determines the quality of the X-ray production. Okay, so to be summarizing this part and making it more understandable, just remember that when you increase the milliampere and when you increase the current in the circuit, because more number of X-rays are produced. Okay, so that is the relation between milliampere and second. More the current and more the time, the more the X-rays are produced. Now, kilovoltage. The kilovoltage, it determines the number of photons or X-rays and also the quality, whether it's a high energy or whether it's a low energy one. Okay, so that ends the